Hi everyone, and welcome to another Octagon video. Once again, this is a plant video, and in this video we are going to start talking about a pump. So taking off from the tank, we can see that we're using the same connector as before, and you're going to see a lot of similar parts, but overall this pump is going to be manually cranked over. It is a piston pump, in that we're using a piston to basically create pressure, and it isn't finished, so there's actually another piece missing on top over here, and sitting on top of that, kind of opposite to this up here, is going to be another one of these quick release valves that are also on top of the tank. Showed prototypes of the actual tubes that we're going to be used to interconnect everything, but the idea is just to kind of start off with the pump, because like everything else, and this is becoming a recurring theme, version 1 of everything sucks. And as always, or what's becoming quite regular, is we're actually going to go through the graveyard and kind of explain how we arrived at the design that we're at. But overall, if we look at this pump, what are we looking at doing? We're looking at a fluid pump to be able to fill our good old Octagon tank, which is sitting down over here next to my brand new rolls of filament. I've taken off the valve on top to basically use it on the thing, but eventually imagine you can actually pump something into this tank. We want to be able to pump water, we want to be able to pump air. Ideally this tank, by the use of this pump, is going to be able to accumulate pressure if we're talking about a compressible fluid or a compressible gas like air. But first we got to build one, then we got to get it to work, and then after that we can get it basically accumulating pressure. And obviously we have all kinds of valves and seals that we need to get working, as well as springs across the whole board here. So still lots of work before everything becomes functional, but first we'll start by having something, and then we'll get it working. So if I look at the functioning of the pump, I'm going to lay it flat, because again I'm doing one-hand operation. You have this handle here that is turning a very big gear on the inside. Then we have another small gear that turns a crank, and then we have a crank arm that basically actuates a piston, kind of like a locomotive engine. It'll become very obvious when I open it up. And so far the only thing that you'll be able to see before we actually get going with the disassembly, and I'll try to get in here if I can, is if I crank the handle over, you should be able to see the piston come in and out towards us. You can see it a little bit. But in here we're going to talk about some adventures in 3D printing. You kind of see the piston coming in and out. It does 3 cycles as I do 1-foot evolution on top, but we'll get into that. So I guess the first thing to key off is, we're using the same quick release clips as we're using for the quick disconnect. I made a mistake in printing. I forgot to print the little dimples that appear here that fit into these individual slots. That's just a design mistake on my part. And I'll start off by taking this guy off, because we're more familiar, or there's some previous videos on how this works. One of the main reasons why version 1 of this guy, I'm going to say, sucks, is that made plenty of design mistakes on this. I'm going to say less design hours before you start to print, and less iterations, more mistakes on version 1. So this is going to be a bit difficult to do with one hand, so I'm going to switch to something I can do with 2 hands. So these things need to come out so that I can actually lift. Let me lift the top part of the valve quick release buttons. Same mechanism as before. This piece here is different. It's been adapted. There's no ball at the bottom of here. I talked about this being cut up in the previous video. I never showed it. Here we can see it. That has to do with the latest version of the gears. But anyways, we're not here to talk about that. So I'm just gonna take this out. And if we compare this to a previous design that I have over here, we obviously don't have a ball because this is the intake for the actual pump. So now that we've got that out, we can continue the disassembly of this pump, which basically has to do with, you know, these two pieces here are going to come apart and we're going to see the internal mechanism. And before I need to do that, I actually need to take that up because that's holding these two things together. So very similar to the bottom pieces, I just take the four little latches, I open them up so that these things here are parallel, and then I can just lift it up. Now, one of the many mistakes that I made, so this guy here has got some mistakes, which is very unfortunate. The only real difference between that and the previous latches is that these pins are way longer than the previous ones, because this is obviously way thicker than this guy over here. But effectively, you know, we're trying to maximize the reuse of as many components as we can. So this little latch is the same. It fits in the same way as before. Obviously the pins are just longer. So this overall piece is reasonably important. I'll talk probably more about it as we go on. But what we have is the piston actually comes in up in here. And then we have an intake and an outtake. And I'll talk more about that a little bit later on. But one of the interesting designs of this, and I'm going to have to get into the CAD files, is that this comes in, the fluid actually goes around the piston, and then actually comes up in a hole around here to actually cool the whole thing down. So 3D printing and pistons are not a good idea. And then this is going to come in and be covered over and sealed so that all the liquid comes back down in here and comes up in here into the actual pumping mechanism. So again, it's basically an internal cooling system. It's not absolutely required, but I'm forecasting, after having looked online at all of the other failed, I'm going to call it, you know, if you can create 3D pumps, there's lots of videos on YouTube that show you how to do that. The issue is that all the pumps fail because they can't take pressure. And once you get the pumps working at a very high rate, the plastic actually starts to melt. So if we take the intake fluid, which I'm hoping is going to be cold, you know, we'll be able to actively cool the piston cylinder so that it doesn't melt and we get a longer life, or we can basically operate at a higher revolution. So we'll put that aside and we'll get into the actual internal mechanism. So here we have our piston. And if I crank this guy over, it's going to kind of look clunky right now. But if I crank this guy over, you can see the piston comes in and out, or up and down. Obviously, without the piston cylinder head, you know, it just flops around. But we can see that it is going up and down and up and down and up and down. So this assembly might become a lot more familiar when we basically take the whole thing apart. So let's do that. So eventually, crack it open. Here's what we have. I've obviously made some mistakes that I had to cut out. But again, this is version 1. And here we have the big gear that I was telling you about. If I take that off right away, we can see here that we've got a crank and we've got a crank arm that comes around. So again, looking online at how this whole thing needs to work, the length of this arm versus this diameter, it's obviously got to be bigger than 1:1, or else we're going to get into, you know, this angle is going to be less than 45 degrees and we'll probably get into trouble. They recommend anything from a 5:1 to an 8:1, and I'm more along the lines of an 8:1. And I believe the stroke, or if I look at the center of this on this side, you know, the distance over here, I do believe that it's 3 centimeters or 30 millimeters, and that turns into the displacement of 30 millimeters up top. So in general, what I use when I'm trying to create a seal, I use 12 millimeters. You know, so if we use that as a reference in terms of how high this goes up before it starts to come down again, you know, we're getting more or less 3 times that distance, I think anyways. So, but again, looking at the CAD files will reveal all. We can see that we got a couple of slots for the piston rings. I've printed these up a while ago. Like everything else, basically they're too big. So I'm gonna have to put in the TPU back into the 3D printer and go on a rampage of printing various, shrinking the diameter of these things, increasing the extrusion, so that I basically get, you know, a more consistent one that will fit in here and provide the right tolerance with the actual wall. So in general, on all of the designs across the board, be it even this little guy here, which once again has these ridges to be able to add in some washers or some O-rings. The difference in diameter is 1.6 millimeters. So that's 0.8 millimeters on each side. These things here are the radius of the tube. If I was to cut this and pull it out straight, the diameter of this is 2 millimeters or 1 millimeter radius. 1 millimeter indented, 1 millimeter out, and basically, you know, 0.8 and 0.8, so I'm compressing this thing by 0.2 millimeters. I'm going to keep the tolerance fixed, and like I said, I'm going to play with the stretch of these things. So if this is, I'm going to keep it at 2 millimeters in diameter, 1 millimeter in radius, and as I make this diameter smaller and I have to stretch it across this or stretch it across that, I'm expecting the outer diameter of this to be smaller and the tolerance to go down. Anyways, play around with that until we're successful. Continuing along the disassembly, I'm just going to go through what we covered quickly and kind of skipped over. So, you know, one of the big things with 3D printing that I've kind of learned in YouTube is that I'm going to say an axle is not your friend. So what I'm doing is very big parts. You can see that I've got a bit of a ledge here, so that when this gear is sitting in here, it actually rubs flat. And once again, the edge of the gear here, bad idea to have it rub against a specific surface. And if I want to look at what I'm using as an axle, you can see that this is a, you know, this overall wheel here actually sits in here. I get very good contact with the gears now that they're a lot bigger than the internal workings of the quick release. I have been able to get these to skip very specifically when I have the seal. But you know, you can hear here I got a little bit of tolerance, a little bit of play, using my typical 0.4 millimeters on either side. So all the diameters are 0.8 millimeters bigger to create these tolerances. Might have to tighten that up eventually, but putting something together right now seems to be good enough. It's not the biggest of my problems, but obviously I had to add this on top so that this would work out. So continuing the disassembly, I obviously have a hole over here for this to seat in, and once again, big fat axle, right, sliding in here. With my 0.4 millimeter tolerance, the idea is I don't want to have to put in grease or anything like that, and I'm expecting all of these things to just kind of wear out. So everybody in YouTube 3D prints and sands, I just consider that to be extraneous. If this thing sits in here and just, you know, over usage, it's going to wear its own piece out. And once again, I find this PLA Plus to be a little, I'm going to call it greasy. There's like a bit of an oil residue almost, it feels afterwards. So I don't foresee it to be a problem until it dries out completely. But that's kind of the philosophy of Octagon is, you know, very cheap 3D printer, you know, filament that you make yourself, print it and go. And the only real thing, you know, that we want to do is get a good design. So that's where all the time is spent. That's where all the value is. And if we look at a lot of the quality of some of the things, you know, you can keep fiddling around with the design and reprint and reprint and reprint and get it perfect at the design stage. Or you can print and say, oh shit, I made a mistake, and then just sand it out, which I consider, you know, it's good to get a product right away, but it's not necessarily good to get something that is useful that other can use. So taking this apart, it's actually reasonably simple. I just pull this wheel off and I have that axle, like I said, 1.5 centimeters from center, you know, 1.5 centimeters on the other side gives me the overall stroke. So if I look at the distance of where the center of this guy is, and the distance between that and that from left to right is, I think, 30 centimeters. But that same distance equivalents to the stroke. So we're going to get it topped up, right? Topped out and then bottomed out. So that's what we have here. And here I'm going to pull out the piston arm. Now I'm going to get a little bit more in terms of how this box here is built, but we'll do that on reassembly. So one of the important things is that I actually have bearings. So once again, the Nanobot was my first foray into 3D printing, and I designed a bearing there, and here it is. Is it required? Is it going to satisfy? Is it going to work? Or is it really required and everything else? I don't know. I'm doing it because everybody in YouTube puts in steel bearings into their projects. Let's just see if this helps. If this wears out and we just need to print another one as opposed to having to print a whole other crank arm, then probably worthwhile. But the whole idea of getting to this point is actually to get to this, the piston and the crank and kind of how this whole thing is put together. So before I do that, I'm just going to drop the piston down, and for the last part of the disassembly, I'm going to talk about this piece over here. So, if we look at the equivalent of this in a combustion engine for a car, right, you're going to have whatever, V8, so you're going to have 8 cylinders, and you're going to have 1 crankshaft, right, and this is effectively your crankshaft. So right now what I have is one of these bearings. I just sit it in there, comes in here, put our handy dandy crank arm over top, add our bearing, right, and overall now I've got this square hole and a square stock, and here we have the overall assembly. Very simple. All my tolerances are the same, right? You can see there's a bit of play in here. We want it nice and loose. We want it to, to basically to float. And if I turn this guy around, we should see that piston going up and down as I rotate this out. So again, crankshaft, very large diameter, right? So that we can do that. This comes right out of the printer, no sanding, just stick it in there, and hopefully with time and usage it'll actually just rub whatever material out that is going to get in the way. I want to get into this assembly here because that's going to introduce us to the graveyard or the scrapyard, because that was an interesting venture. But before I do that, I just want to talk about the crankshaft one more time and just focus in on the slot that it fits in. So we can see here we have a box that is actually the actual width of the crank arm. And if we're looking at keeping the piston orientated, obviously the cylinder head does all the job, but obviously we're taking advantage of the crank arm. So if I put the two boxes back together, right, you can see here that I've got a slot in there where the crank arm is free to travel, and that comes down at the same diameter to these guys over here. Fairly simple design. All of this, obviously, I'm using 20% infill just instead of the regular 40%, just to try to save on a little bit of plastic. Made some mistakes over here. The zigzag infill is not the best. I want to switch to cubic so you can and hopefully solve some of these defects over here, this little line, which actually has to do with how this joins up with this guy. And obviously I'm getting a little bit of elephant's foot, I think they call it. Which is kind of at this level. And if I look at this piece here, this one, I had an early prototype and I forgot to save the latest file, but I forgot to put the holes, so I had to cut these out. Broke the actual the stock that comes out of here, so I actually cut it out. So overall, lots of compromises, but kind of gets me started, and we're just kind of working on a go-forward basis. So now I want to focus on the actual the piston assembly, because obviously what we need to do is get this thing to work. And you can see here, I've got a little triangular piece in order to get that going. And I'm going to switch to the cable view. so that we can actually take this guy apart in a bit more detail. So the idea, you know, once again, we're playing with the limits of the plastic. I want to be able to pull these things in. This is not designed to come apart. Effectively what we have is that, and if I take these two halves out, I'm going to introduce the first piece of the graveyard with a failed approach. I'm going to get into this guy later on, but basically if I pull this guy, it's a different diameter, but I'm going to get this. So again, the crankshaft is fully symmetric from top to bottom, and I've got a bearing, right? Put the crankshaft, put these things in together, slide it in, it clips into this thing here, and we have a permanent assembly. How tough is this right now? I don't know. I can use pretty much all of my strength, right? I haven't had it pop out, I haven't had it break yet, but you're gonna see that I had to do a bunch of iterations making this bigger and bigger and bigger until I got to something that at least is functional and worthy of starting a video. So we're moving right into the graveyard. We're gonna basically look at what this whole idea is by basically showing you the first version of this. So the idea was to grab the way that this thing bites onto this thing and do a whole bunch of them around and have them bite towards the inside. So, you know, this was inspired maybe by the tube, you know, and having something like this that grabs onto the tube. This hasn't worked out for me as per the tube video, another version 1 that sucks. So we'll call this version 0 or 0.1. And again, this was so small and is so flaky that it started to fall apart. So again, the inside of this is the same as that. So what do you do when this is too small and it starts to break, like this little part that's kind of flapping in the wind on the inside here? Well, you just make it thicker. So by making it thicker, I thought I was going to solve some problems, but at the end of the day, as soon as I popped it in, all of the heads came out, right? So here I am, and you know, these are a little bit sturdier, but again, didn't get a result. I was hoping I could slide it in like I would this guy, you know, it would snap in permanently, snapped in, can't take it out, no cigar. So what do you do when this breaks? Well, you make it even bigger. And here I turned around and I said, oh my God, I broke my 3D printer. So again, this is thicker than this guy, but it didn't print. So what's going on? So what happens is that when the printer gets to this point here, it only has all these little individual stalks to do, and the printer head is continuously retracting. The gears that retract and pinch the filament end up wearing the filament out, and there's like little gear marks on the filament, and the filament ends up getting worn out, and then it doesn't retract anymore, and it doesn't push in either. So that's what we ended up having over here. So you could see exactly where this started to happen. So when I was printing down over here, it was nice long runs, the filament was running through, you know, the gears weren't going back and forth over the same thing. Then it did it for whatever this rise is, and by the time it got to this, it went to shits. So again, this is thicker than that. I tried tree view support, it didn't quite work out. So at that point in time, I just had to scrap the approach and I moved to this design. So if we can call this, you know, 0.1, you know, this would be 0.11, or sorry, this would be 0.10, 0.11, right? 0.12, and let's just abandon the whole thing. So when I moved into this one, once again, minimalist approach, first thing I did was this guy. And you can see how fine it is, and right away, right, these things here snapped off right away. So what do? You go back to making it thicker. You know, so what does thicker do? Well, lasts a little bit better, but I started getting the same thing happening as before. So even with just 4 things, it was retracting enough to start causing the same problem, but obviously it started causing it a lot higher. So if we look at how thick this is, it's thick enough to basically, for that retraction problem to start happening. There's a lot of videos on YouTube that talk about this. I heard about it. This retraction problem, I didn't basically whatever. Not that I didn't believe it. I just said, okay, you know, note to self, I'll just remember. And finally, it's happened to me where I've actually had to change the design because the 3D printer, or my 3D printer, will never be able to print this unless I change the orientation, which kind of defeats the purpose. So when we get into this, I think I'm at 4 millimeters at least, or maybe even more, maybe 6. You know, it has enough of a run here, then it retracts a little bit to break the filament and then start extracting on this one, and then it starts to work. So most of these here, my goal is to do 100% infill. This is 2 millimeters thick, 4 millimeters thick on the piston head, 4 millimeters thick on the wall, so that it lasts. And then basically, yeah, but sometimes some of these I ended up printing with 40% infill. So that's the graveyard tour, or the important graveyard tour for today, or what brings us to the graveyard or the junkyard. And with that, I'm going to basically talk about a few other failed prints so far on this project. So once again, talked about the main gear, this guy over here. This thing here has one of these guys on top, which broke off. So to see how that looks like, I'm going to introduce this guy over here, and we can see how it's supposed to look like, you know, when we don't have, when it isn't broken off. So that's the way it looks like. Got a hole in the actual handle, right? This is a print in place sphere inside of a sphere, right? So this prints all as one piece and can never be disassembled unless you break it. And this guy fits in here. The funny part about it is, the first time I printed it, I got this thing wrong. Tried to jam this guy in here, and that's how I broke this guy. And just to talk about, you know, design mistakes, you're putting two things together. In Tinkercad, you know, you get a 0.2 or even a 0.01% millimeter difference. The slicer thinks it's two independent pieces, and these two things came apart. 40% infill, most likely, maybe it's 20. But obviously that was a failed print. That was a bit of a disappointment. Even worse than that, that wasn't actually even my first try. Here was my first try, and I ran out of filament. So imagine that. So, you know, design it up. I've got the, you know, the case designed over here. I'm all excited, ready to get going. You know, I've got my piston assembly. I've had this kind of sitting around, hanging around like this, you know, wanting to engage a gear. So I finally print the gear and ran out of filament. Printed a second time, make a mistake. Oh, well, at least I got something that can fit in. Unfortunately, with this separate, it doesn't fit in that in any way. Break this thing, print it a third time, get this guy here going. Once again, I just kind of hold on to the gear, turn the hand a little bit, snap this thing off of this guy, and then I ended up cutting it out to basically, you know, embed it in. Luckily, this part here is too long, or longer than what it needs to be, so that I can still get it going. But I'm going to include this into the design and then have this sticking out so that we have maximum strength. That is, this thing here will only serve to slide this in, and basically hopefully the force is all on the outer edge. So yeah, so that's that gear, and the graveyard tour ended for that specific part. The last part that I want to bring up is this one. Ran out of filament yet once again. So that's the same piece as this guy over here, and you can see the only difference is that if I put them next to each other, I ran out of filament. But the interesting part is that I kind of caught it this time, and I basically put in new filament. And 3D printers are pretty good at recuperating, except for this bowing process. So anyways, I thought this is kind of cool because replaced the printer, let it go, and I just wanted to see if it would recuperate, and it didn't, because once it separates from the printing bed and it starts to wobble, you're going to have problems. Here I've got my first solar panel that I'm printing, and you can see that even with a raft, I'm still getting a shitload of bowing, and that's, you know, not going to work out. But again, that same bowing effect is kind of affecting me here. So what I like about this guy is that obviously this hole is a lot bigger because we didn't, it's got stopped kind of just after this elevation. So I'm going to use this for the reassembly so that we can actually see the piston head coming up and down quite a bit more and explain a little bit the piston assembly. So in general, what we're going to have is sitting on top of this guy is a ball, and sitting on top of this guy is a cone or a funnel. So if you look at a combustion engine, a motor in a car, a petrol or diesel motor in a car, you're going to see that the valves and the piston heads are little triangular or little cone-shaped things on the top of a stick that basically gets pulled up in order to basically seal, to make a seal. So that's what we're going to have to seal in the intake. And I don't know if you could see that, but well, I can see it anyways. I'm going to try to point it out. So if we look at this guy over here, you can see that we have, right, that is a cone that's out of there. So effectively we're gonna have like a funnel and with a really long stick. Obviously the funnel is not gonna be hollow. That is gonna basically seal this up. And then we're gonna have a ball, just the same design as the ball joint, as the ball valve for the quick disconnect, sitting on top of this guy over here. So when the pump cylinder goes up, right, a spring is going to close this guy, and then the pressure is going to release this ball, and then we're fine. The pressure is also going to close this guy. The springs may not be required, but I believe the springs are the difference between a self-priming pump and a non-self-priming pump. So more conversations on that maybe later on, but again, this is one of the reasons that I wanted to do the first video. So again, this cavity in here is completely not required. This is 12 millimeters, and the only reason that this is here, there's going to be a 2 millimeter gap on top of that when this lid comes on top, and the hole in the back here all the way around is for a self-cooling mechanism. Now you might be able to see the hole in terms of where this, you can see that this goes down here and stops, and it elbows into this connection. And then on this side, this doesn't go all the way across, but it's like two glass walls on either side. Again, the CAD file is going to be the best to show this. But if I slide a piece of paper in here, you're going to see that the top part of this void is going to connect to the bottom part. And there's a layer across here that separates the two. So what ends up happening is that fluid comes in here, okay, comes into the piston wall, comes up, comes around the piston wall on either side, down over here and across the top. It'll come up here, and then it'll come back across here, and then it'll come through here. Once again, the CAD files, because you can't see it, is in here, and the little horizontal component that connects these two is in the exact same shape as this guy over here, so that the system doesn't generate any inflow. So once again, there's a void equivalent to this that's completely enclosed below the midpoint of this part. So we can review that a bit later, but for now, what I want to do is basically reassemble. I'm going to take the parts out of this guy, reassemble it on the part that was the failed print, and then after we're reassembled, you can see the piston going up and down, kind of explain what mechanism is left to do in terms of design, and then we can end the video. Okay, back to ground view. But the whole idea of the pump is to be able to hold on to it, you know, with one hand. You know, maybe I'll have to put something to allow your fingers to go in so that when you so here, hopefully you'll be able to see a bit better, you know, the piston top, and as I turn, the piston goes down, piston top, piston goes down. So the idea is that one valve, right, when the piston goes down, it's going to create suction. The suction is going to basically open up this side. This side is under pressure. There's going to be more back pressure. So when that happens, when it starts to come down, the ball is going to come in and tap that hole. And because this is low pressure, this will open itself up, and then basically the fluid will come in. That's the theory anyways. Let's see if we can get it working. But effectively, this is getting pulled up all the time, and the ball is getting pushed down all the time. And that just kind of gives it a little bit of a preference. So when this is up and we're starting to push, it's just going to push the cone in, up more as it pushes the ball. But since the ball's got somewhere to go, it's actually going to move. That's the theory. And then when there's suction, it works the contrary. So to close out this video, just want to talk a little bit about the cylinder head. So did a lot of research on YouTube in terms of pumps and 3D printed pumps. Got a lot of different results. Most of them leak. So this is why I'm going to basically try to work with the piston and O-ring design. There's going to be a lot of friction in there and consequently a lot of heat. So building cylinder walls, anything cylinder, motor, pump or whatever, you know, Tinkercad breaks everything down into a bunch 64-sided shape or polygon. Is actually not a perfect circle. And again, we can sand it down to try to get a nice tolerance and everything else to try to create pressure. I just want to use TPU, again, to not have to do any sanding, stick it in there, and we're going to get friction. And what's going to happen is that everything is going to start melting. Or, very specifically, I think the melting point of TPU is close to 200 degrees Celsius, but it starts to deform, or its elastic temperature is 50 or 60 degrees. And if we run this pump really fast, especially with an electric motor, this is going to heat up. So part of the design, and it's probably best explained with CAD files, is that I actually have cooling built into the wall of this cylinder in this piece. So if I grab my trusty dusty handy dandy screwdriver and I put this in here, we're going to see that I run into something, which is obviously way more. It's about halfway through or even less, and it's the same thing over here. So what I have is that this comes in and goes off to the left, and this comes up and goes off to the left. And I have a cylinder wall divided in two. What do I mean by a cylinder wall? If you look in here, you've got a little crack here all the way around, and that's for the cooling to come up. Okay, and that only goes down halfway down the sidewall. So if you see, there's a bottom there. It's not down here, it's actually up here. And we have all the fluid coming in from the side, wrapping around the outer perimeter of the cylinder, then going up through a crack on this side, and then it'll come back around the other side. And then the top piece fits in, and it's going to have O-rings sticking on this wall. Obviously my little O-ring sticking in here, and this hole here is the same diameter to accept one of these guys. So, and then on top is going to be the mechanisms with the actual valves. So the main purpose of the video was to explain, well, the cylinder head and the cooling, because the next video we're just going to focus on the valving mechanism, which is actually what's going to get everything to work. And once again, I think the springs are becoming a very critical part of the overall design of everything that I'm doing here. So I'm going to have to do some work on that. But in general, you know, this development I'm expecting to be something that's very important, very unique. So effectively, new fluid comes in, cold water comes in, cools the piston wall as everything is actually flowing through. So that's the idea. Lots of work before we actually get this thing complete as a mechanical device, working for water and or fluids. or other fluids, as in air. If we want to look at air, I wanted it to start taking pressure. Again, there's going to be a lot of work there. Then we want to make it electric. And then what we want to do ultimately is use this and turn it into a refrigerator. So why is that? You have to look at and understand what we're looking at doing as Octagon from a space ecotourism perspective. But let's just say we have a long journey to go, and in terms of the pump, this is the start. Thanks for your attention, and we'll see you in the next video.